Okay, so this is the next in our series of videos on systems of linear equations. So in this video we're going to go through sort of the basic terminology and notation that we will apply for linear systems. So a general system of linear equations can be a pretty complicated looking thing. All right, there can be any number of equations, any number of variables. So this might be, hundreds of thousands of equations relating millions of variables. This could be some very complicated problem that we're trying to solve here. And one of the things we'll see is that even for very, very, very large systems like that, there are computer algorithms that work reasonably quickly for solving these things. Now, for extremely large systems, the algorithms that we learn in this course, they're not good enough. It turns out that there are other algorithms which solve systems very, very fast, but only approximately, and you can sort of decide how much error you're willing to accept in your solution if you get there much, much faster. And by error, we're talking, the value of x1 might be off by 0.001 or something like this. So a general system looks like this, right? We have you've got a whole bunch of variables, x1 up to xn. Each equation, the x's are being multiplied by some numbers, right? So a11. Notice that there are two subscripts here. One subscript, the second subscript tells you which variable, right? 1, 1, 2, 2, and n, right? The first subscript tells you which equation we're talking about, right? First equation, second equation, third equation, down to the mth equation, right? And then we have some constants on the right-hand side. So these are called the coefficients. Notice that one thing you get, this is going to be important for us later on, you can form a matrix of coefficients, right? So you can form a matrix A whose entries, Aij, are simply the numbers that you see up in this system of equations. So one of the things that we'll do when we're developing our methods for solving systems is rather than work with this system itself, we're going to work with matrices. We're going to work with this matrix of coefficients, and we'll see how to solve the system by working with the matrix rather than with the system itself. So a bit of terminology on this slide. A consistent system is one that has at least one solution. Okay, it might be one solution, it might be an infinite number of solutions, but there's at least one solution. An inconsistent system is one where there is no solution at all. Now, where do these systems come from? There are all sorts of practical applications to solving systems of equations. Ones that you might see in your other science courses here would be something like a problem involving electrical circuits in a physics class, balancing chemical reactions in a basic chemistry class. In economics, you might study input-output models. And there are other problems, Markov chains, which involves matrix multiplication, but there are still some systems you might have to solve there. There are a number of situations where you have to solve some system of equations, right? Any time that you're dealing with some number of variables and the relationships among those variables are linear, you're dealing with a linear system. There are lots of mathematical sources from within this course that we've seen that lead to systems of equations, right? Intersections of lines, we saw that when you're back in chapter 3, when you tried to determine whether or not two lines intersect, you ended up with 3 equations in 2 variables. Intersection of planes, that's 2 equations in 3 variables. Any question involving linear independence or span is really a question about systems of equations. We'll see that when we move on to chapter 6, right? Problems where you're trying to compute a basis, often you have to compute, you have to solve a system of equations, right? Solving matrix equations, these ones that might come up from, say, working with matrix transformations, you're solving a system. Also related to matrix transformations are the column space and null space. Computing these, again, leads to systems of equations. Lots of problems in linear algebra, which can be stated rather abstractly, eventually boil down to simply solving a system of equations. Okay, so what are some basic examples? We saw some of these previously. Okay, here's a system of two equations in two variables. How would you solve this? Well, we could solve it graphically. I could draw the lines if I want. Actually, why don't I'll let the computer draw the lines for me. Okay, so here's an example. Here are the two lines, right? So the first line F there. So this is the graph of 3x minus 2y equals 4. The second line G, that's the line given by minus 2x plus 5y equals minus 2. And I could ask for the intersection between these two, and it's this point here, right? This software, by the way, this software is called GeoGebra, and it will do things like intersections for you, right? I can say, you know what, I want the point of intersection between this line and that line, and it'll do that for me. Of course, I already did it once, so I don't need to do it again. Okay. So we get that point. The maybe one downside here is that GeoGebra doesn't give me exact answers. It gives me decimal answers. 1.4545, 0.1818. Those sound like repeating decimals to me. Let's see. Let's add a few more decimal places. Oh, those definitely look like repeating decimals. So repeating decimals, those came from some sort of fractions, so we got some rational answers. What are the exact answers? If we wanted to give these things in fractions, what do they look like? Well, again, we haven't developed systematic methods yet, but let's label these 1 and 2. I could do equation 1 times 2. That would give me 6x minus 4y equals 8. Let's do equation 2 times 3. That's going to give me minus 6x plus 15y equals minus 6. Let's add those up. Right? Now 6x minus 6x, you can see why I want to add them. Those cancel out. I get 11y equals 2. That's telling me that y should equal to 2 over 11. Okay? So 2 over 11, that must be that 0.1818181818. That must be 2 over 11. What about x? Well, let's take that value, y equals 2 over 11. Let's plug that into, I don't know, let's plug it into the first equation. So 3x minus 2 times 2 over 11 equals 4. So 3x is equal to 4 plus 4 over 11. That's 44 plus 4 over 11, so that's 48 over 11. Dividing both sides by 3, 48 over 3 is 16, so x should be 16 over 11. Okay, so 16 over 11, that must be that 1.45454545 that the software gave us. If we want to verify this, make sure this really is a solution, okay, I've got it on my slides, I must have done it right, but how do we actually double check, make sure that we've done things correctly? Well, if you just want to verify that some numbers actually solve your system, you don't have to go ahead and, if I give you the numbers, right? You don't have to go and solve the system and reduce it down and find out that that's your answer. No, you got the numbers, plug them in. 3 times 16 over 11 minus 2 times 2 over 11 is 48 over 11 minus 4 over 11. That's 44 over 11. That's 4. That's what I'm supposed to get. Okay? Minus 2 times 16 over 11 plus 5 times 2 over 11 is minus 32 over 11 plus 10 over 11. That's minus 22 over 11. That's minus 2. Works in the second equation as well, right? So when we say that these values are a solution to the system, we mean they don't just work in one of the equations, they work in all of the equations. In this case, there are 2 that we have to check, so we plug it into both. Okay. Here's another example, 2 equations, 2 variables, no solution. Again, we can see this graphically. Why don't we get a solution in this case? Let's open up this guy. What do we have? Okay, nothing yet. I haven't plotted the lines. Let's plot the first line. Okay, x minus 2y equals 4. There it is. The other one, the software simplified it for me. What was my other one? Minus 2x plus 4y equals 0. If I plot that line, there it is. those two look suspiciously like parallel lines, right? Those are lines that are never going to meet. So it makes sense that there's no solution to this system, right? We've got two parallel lines, they never intersect, so we can't solve the system. How do we actually see that algebraically, that there's no solution? Well, let's do equation 1 times 2. We get 2x minus 4y equals 2 times 4, so that's going to be 8. Okay, minus 2x plus 4y equals 0. Right? We can add these together, right? If the left-hand side equals right-hand side for both of them, then adding the left-hand sides should be the same thing as adding the right-hand sides. And what do we get? 2x minus 2x, we get 0. 0 equals 8. Well, that's a problem, right? 0 is not equal to 8. So there's no way to solve this system, right? The simplifying the left-hand sides, everything collapses down to 0. The right-hand side doesn't collapse down to 0. So there's no way to solve this, right? 0 can't equal 8. So there's no possible choice of values that is going to work for this system, right? No matter what you plug in for x and y, there's no values of x and y that are going to make 0 equal 8. 0 is just never equal to 8. Okay. Here's one more example. Two equations in 3 variables. Let's say I want to solve all solutions to this system. Okay. This takes a little bit more work. What we might do here, there's a few ways to do it. One way we might do it is we might do this. We might say, okay, here's equation 1, equation 2. Let's do equation 1. Let's do kind of something like this again. Equation 1 times 3, and we'll do equation 2 times 2. Actually, let's do not just 2, but times minus 2. So 6x minus 12y minus 3z equals minus 18, minus 6x minus 2y minus 4z equals minus 8. I add these up, I'm going to get, what am I going to get? Minus 14y, right? The x's cancel, minus 7z is equal to minus 26. And then I might try to say, okay, you know what, why don't I solve for, let's divide through by 7, maybe divide through by minus 7, so 2y plus z is equal to 26 over 7, right? So z is equal to 26 over 7 minus 2y. So I can write z in terms of y. I could then say, well, if I can write z in terms of y, and then I could probably solve for x in terms of y. I could take this, I could plug it into here. But the best I can do is I could eliminate y, right? Or I could eliminate z, right? So I could plug that in there. I would get 2x minus 4y minus 26 over 7 plus 2y is equal to minus 6. And so I could solve here for x, right? I could get x would be equal to, so I've got minus 2y, bring it over, divide by 2y, and then I've got minus 3 plus 13 over 7, right? That's some number. Okay, and so now I've written x in terms of y, I've written z in terms of y, but I can't, there's no way to kind of solve exactly for x, y, and z here, because y can take on any values I want. In fact, choosing any value of y would give me a solution, right? If I put y equal to 0, that would give me a solution. Putting y equal to 2 would give me a solution. I get an infinite number of solutions. What do those solutions look like? Oops. Why don't we plot them? So let's open up this guy here. Okay. All right. So each equation defines a plane, right? Here's the first equation, right? I plot that. You can see that I've got a plane sitting there. Okay. I do the second equation. I get a second plane. You can see now there's those two planes, right? And what are the solutions? The solutions are all the points that are common to both planes. And you can kind of see that there are some points common to both planes. What are they? Well, again, I can ask the software to intersect my planes, and I get everything along that green line. We can see that green line lies in both of the planes. It lies in the red plane, lies in the blue plane. If I hide the planes, I'm left with a line. Okay, a line sitting there in space. And every point along that line is a solution to my system, so I get an infinite number of solutions in this case. Alright, that's it for this video.